Hello, my name is Yuzhou. I will be introducing you a new concept in this training course called hybrid modeling. You can easily see its meaning from its name, which combines two techniques together, including data-driven and Earth system models for higher accuracy and deeper understanding, which brings about a new era of innovation and insights in Earth system science. I believe you have already learned a lot from previous sections about process-based model. In general, you can simulate all the processes in this beautiful picture created by Ward et al. Process-based models in Earth system science describe systematic change using empirical equations and offers process-based understanding about the changes in the climate, ecosystems, and their interactions across space and time. By using process-based models, we can simulate historical dynamics and predict future changes both over long-term and short-term scales. This is a simplified workflow of a process-based model. So first of all, you have those input drivers that can be spatial temporal rasters, graphs, or temporal series data. You pull this data into the process-based model that is constructed by the scientific equations and different model parameters. And with the model, you can generate different response variables that you want in different formats. So basically here, the process-based model is a glass box. We can easily see the structure within it. However, we all know that Earth system models sometimes are difficult to represent the accurate dynamics of the ecosystem because their ability to do so are limited by their specific simplified scientific equations and empirical model parameters. More specifically, the equations and parameters adopted by most models were derived from limited experiments and observations in specific geographic contexts. But we all know that parameters, or even these equations, may vary spatially and temporally. Unfortunately, traditional hand-tuning and dissemination that we learned from previous sections are computationally infeasible to get the optimized parameters in this case. In the contrast, machine learning and artificial intelligence models have impressive ability in capturing complex nonlinear relationships between target variables and their driven factors, which is more accurate than most process-based models. Such models are increasingly applied in the Earth system science as well. However, the primary limitation of utilizing these techniques in science is their nature as black boxes that present difficulties in interpretation and also the lack of physical significance and scientific justification. And they also have the risk of generating inaccurate results when applying the model beyond their training domain, which is also called the out of sample scenarios. So therefore, it's also difficult to use for prediction. So there is an opportunity for parameters and equations of Earth system models to be refined by taking advantage of machine learning and artificial intelligence models. In current Earth system science, data availability has been increased dramatically in the past few years. That there is a trend commonly referred to as big data. The increased amount of data came from lab experiments, field measurements, drones, and satellite observations. We can take advantage of current data availability to improve our system models in terms of parameterization and process-based optimization by incorporation of data-driven method, which is a topic in this section called hybrid modeling. The Nature paper by Rehenstein et al. In 2019 listed several aspects that characterize the hybrid modeling, including improving parameterization, replacing a physical submodel with a machine learning or artificial intelligence model, analyze the mismatch between model and observation, constraining submodels, and surrogate modeling or emulation. For example, the parameters in the assist model may vary spatially and temporally. Uh, in the training course, one section by Fontal proposed a hybrid modeling approach called PRODA, which integrates data simulation and at block scale and machine learning to extrapolate optimized parameters to the global scale. This hybrid model has improved our understanding of changes in the soil organic carbon. This chapter focuses on a hybrid modeling technique which involves replacing a physical submodel with an machine learning or artificial intelligence model and constrain the submodels, using an example of latent heat flux simulation to illustrate this concept. Accurate simulating of surface latent heat is very important in the Earth's models because this is indicate how much water will be released by evapotranspiration processes. So for example, here, this is the framework of TICO model that you can see in evapotranspiration um, that indicates the water flow is coupled with different carbon flows that the simulation of it will increase the uh, accurate simulation of carbon cycle as well. So in the physical process, the evapotranspiration is controlled by the surface energy balance between the income radiation and the heat release from the ground surface, and also controlled by the surface canopy properties like the roughness and the wind speed to control the water release rate from the canopy surface. So in most Earth system models, this process is represented by a Pomer-Montis equation. That the Le here is the surface heat flux that is controlled by the net radiation, soil heat flux, and other parameters. I won't go to details. It is explained in the book chapter. But I want to emphasize two parameters here are aerodynamic resistance and bulk surface resistance. These two parameters are critical parameters in estimating Le, but in most assist models, they are calculated based on empirical knowledge. The transfer of heat and water vapor from an evaporating surface into the air above the canopy is determined by the aerodynamic resistance here. And the bulk surface resistance often has these two descriptions. Since the values of parameters used in calculating the RS and RA are determined by the vegetation coverage, canopy type, and can also differ across space, it is not possible to get these values for global simulation. And at the same time, the Pomer-Montis equation actually has several limitations. It relies upon several assumptions, including assuming a uniform vegetation canopy, constant aerodynamic resistance, and a uniformly mixed boundary layer. The empirical parameters RA and RS here have limited ability to adapt to changing vegetation composition or long-term climate condition. So as a result, the Pomer-Montis equation does not explicitly account for the state of vegetation and soil moisture, both of which can impact the transpiration rates. To address this issue, Agui et al. Proposed using a machine learning surrogate model to estimate Le directly from environmental conditions, rather than relying solely on a physics-based Pomer-Montis model that includes multiple uncertain parameters. This is a simple case of a surrogate model that is a purely machine learning model. You can see in the left panel here, there is a list of environmental drivers that includes the water availability index, vapor pressure deficit, air temperature, net radiation, shortwave income radiation, ground soil heat flux, potential shortwave radiation, and wind speed. And they put all these drivers fit into a forward neural network model that directly predicts their LE here based on those drivers. The loss function here is defined as the sum of the difference between the observed and the modeled LE at each time step across the simulation period. To train this model, there are actually several hyperparameters should be considered in this neural network model. Most times they include the bench size, linear rate, number of hidden layers, hidden size, and weight decay. There are also several methods to train the model, including grid search, random search, and Bayesian optimization. So we won't go through the details about how to train those models. But you can see from this pure machine learning model, there are sometimes it has the ability to simulate the LE really well, but it lacks the scientific inference about why we have such good LE that we cannot fit those kind of knowledge back into our process-based model to improve it. But it's still going to serve as the surrogate model itself. The second option of building the hybrid modeling for environment transpiration is to estimate those two critical parameters and feed them into the Pullman-Montis equation to get the estimated LE. So here we return the Pullman-Montis equation to get deeper understanding about the mechanistic behind the environment transpiration. What we want to learn from this hybrid model is the relationship between the environmental variables and these two critical parameters, and therefore we can apply these two neural network models to a broader range in terms of space and time to get more applicable model for the future simulation. Here you can see the loss equation is similar to the previous one, which is the difference between the observed LE and modeled LE. But you can see from the design of the hybrid model in this case, it actually suffers from the equifinality issue. That is, the different combination of RS and RA can lead to the same estimation of LE. So this is why we call this case as an unconstrained hybrid model. So to solve the equifinality issue, one way is to restrict the parameter space through model regularization. So here we can introduce one more term from the Pullman-Montis equation and also the field measurement of sensible heat, which is H here. H is more related to the aerodynamic resistance factor that can add more constraining ability for the estimation of this parameter. And we also add one more term in the loss function, which represents the difference between the observed sensible heat and the modeled sensible heat. So by adding one more task into the hybrid model, these two parameters can be better inferred and constrained to be applied to the Pullman-Montis equation. So another way to address the equifinality issue is to integrate the prior knowledge into the hybrid model. So here we can say the RA here, in the previous case, is constrained by the sensible heat measurements. But it also can be inferred by another mechanistic model called big leaf. So we can infer the RA and feed into the Pullman-Montis equation to get the estimation of LE. But also at the same time, we add another term in the loss function to further constrain the RA estimation from this big leaf model. But we sometimes we don't really fully trust the big leaf model estimation. So that's why we add another regulation term here, phi, to give it the weight of the loss that represent how much we can trust the inferred RA from the prior knowledge. So by integrating the prior knowledge, we can also call this hybrid modeling a constrained case. So if we look at those four hybrid models on the axis of data-driven to theory-driven, we can say the pure machine learning is definitely more data-driven. It's purely data-driven actually. So if we add the Pullman-Moniz equation into the hybrid modeling and some prior knowledge into it, those models are more towards to the theory-driven. If we say these four models on the axis of constraints, we can see the pure machine learning and the unconstrained case that has an infinity issue is less constrained. But when we add more tasks or prior knowledge into the hybrid modeling, the constraint ability is increased by doing so. So at the end of this study, Agui et al. Also evaluated the performance of the hybrid models for the half-hourly event transcription, mean diurnal cycle, and the inannual anomalies. You can see those constraint cases and has more theory-driven cases actually have a similar or sometimes even better performance than those unconstrained and pure machine learning models. This means the model captures the in-web transpiration dynamics across different temporal scales. The consistency demonstrates that the models capture the physical accurate dependency of the environmental drivers that controls the latent heat variable. I hope you enjoyed the example I gave in the previous slides about hybrid models. And now I'm listing more future directions about what we should do to move forward this field. First of all, I want to say our ecologists are very endeavored and build a lot of prior knowledge that we can use to guide those machine learning and artificial intelligence models. You may heard those terms like beam or PIM, which are physics or biochemistry informed neural network. And by integrating the prior knowledge, we can efficiently train those models and also gain some mechanistic understanding about those terrestrial processes at different scales. And secondly, I think those machine learning models and artificial intelligence models can be more explainable. That means current models, they are still at the stage of black box. It's really hard to get the mathematical representation between the drivers and the response variables. We need to get more explainable representation in terms of the parameters and the response functions. And by doing so, we can improve the AI technique for scientific discovery. So I hope these are mainly directions that can be investigated in the future. So quiz time. After you watching this video and reading the book chapter, I hope you are able to answer the following questions. First of all, please list the advantages and limitations of Earth system models and artificial intelligence and machine learning models representatively. And how can current Earth system models can be improved by machine learning and artificial intelligence in your perspective? And third one is the most interesting one. I hope you can give one example in your field of work of an empirical model that can be improved by machine learning and artificial intelligence algorithms. That is what we discussed in this chapter called hybrid modeling. And by doing so, I want to know how would you like to design the hybrid model and what kind of constraint you can integrate into the hybrid model. You don't have to code it by yourself after this training course, but I still would like to say the conceptual framework of the hybrid model in your example. And to the end, if you have any questions about the video, about the book chapter, or if you want to discuss some detailed examples about hybrid modeling, please feel free to send me emails. I'm happy to take any questions and discuss with you in the future.